next speaker is Dominik Schürmann, who's going to be presenting real-world attacks on VoIP protocols, ZRTP in particular, work with co-authors at TU.
Okay, do you hear me? Yeah. Is it working? Okay, great. So, welcome to my talk. I'm Dominik, and this is joint work with two of my brightest master students, Fabian and Gregor. And yes, we're looking into ZRTP. It's quite an old standard, but still, it's used. So, we got a nice response from one of the authors of the standard on Twitter. And yeah, he's wondering if we can learn something. So, let's learn something here. Let's look at the current status of end-to-end security in voice calls. So keep in mind end-to-end security, not just client to cloud provider. So public switch telephone network, what we have is not end-to-end secure, it's pretty obvious. Then we have the session initiation protocol, and like RTP and SRTP, it's also not end-to-end secure by design. Okay, let's go on. Then we have something that's called DTLS. It's a datagram transport layer security used to exchange a secret for SRTP. That's end-to-end encryption. And then we have end-to-end encryption and authentication. That's ZIP plus SRTP plus ZRTP. And obviously, for an evil operator, it gets more difficult down the line. So we are looking into this space. So, first, I wanted to introduce what we did in the beginning. So, if we just have zip with encryption only or no encryption, there's a similar setup like this. This is a pretty simplified view with just one zip server. But to get the point across, you have Alice and Bob. They're doing a call. They're using a zip server. And if you're an evil operator, you can do some man in the middle here, some eavesdropping. It's very, very simple. We did an implementation for a zip server Camarillo. And so we're just rewriting some headers in the session initiation and redirecting the call from Alice to a special client that is running on the server, for example. This special client takes the call, does its own call to Bob, and then connects both multimedia streams, and you get your eavesdropping or wiretapping. So very, very simple. It works. On Bob's side, it says Alice and alice@example.com. So how to protect against this? This is ZRTP. So same setup. What the users are seeing is a little bit different. There is something that is called a short authentication string here. It's pretty small here, sorry. So it's just 4 characters. That is shown on the screen, and on the other side, it's also 4 characters shown on the screen. And Alice and Bob need to compare these strings, and when they're different, there's an attack. So they are different, there's an attack here. This is how ZRTP works from a user's perspective. Okay, what are we doing now? So ZRTP is a pretty complex protocol, in my opinion. And it basically boils down to a Diffie-Hellman key exchange that is authenticated using these short authentication strings. To keep these strings short, as the name suggests, they are doing a hash commitment to constrain the attacker to just one try per call. In this paper, we are doing a real-world evaluation of real-world implementations, and we are explicitly not looking into closed networks. We are excluding attacks where we assume that the attacker does some speech synthesis. We are not doing this. We assume that the short authentication strings have been compared correctly. Okay, so in the paper, we looked into the following implementations. There's Acrobat Softphone for iOS, CSIP Simple for Android. There's Jitsi, it's a cross-platform client. We have Linphone, and we have Signal. So in the paper, we have 7 protocol tests and 4 non-protocol tests. And in the presentation, I will just show the interesting results and skip the rest. Okay, so let's dive deep down into ZRTP. This is an extremely simplified view of ZRTP. So the RFC is much longer. So if you look into it, there's on the left side, we have the responder, on the right side, the initiator. they're exchanging some hello messages and random values. That's not that important. What is important, you can find the Diffie-Hellman here. So PVI is the public value for Diffie-Hellman on the initiator side. That's up there. Then we have PVR, it's the responder's public value. And obviously they are doing a Diffie-Hellman key exchange. So this is like the shared secret we get out of this on the initiator side, and this is the one on the responder side. So what's the trick here? It's not sync. It's not. It's not doing this at the same time. They're doing a hash commitment. So instead of directly transmitting the public value, the initiator is transmitting a hash of the public value. So you're kind of committing to a public value without revealing it over the network. And this kind of constrains the attacker to just one try in the beginning. So we don't have like an offline brute force attacker here. Instead, we have an online attacker with just one try. And in the end, the short authentication string is kind of a key duration of the shared secret, the IDs of responder and initiator, and the hash of all messages. Okay, so first thing you need to notice, you need this check. So is the hash that has been committed previously really the hash of the public value that you received? So this is one of our tests. It's a pretty obvious test. And there's one implementation failing it. So Linphone didn't check this. So we don't have the constraint to a one-try attacker. Instead, we have like not unlimited, but we have an attacker with much more brute force capabilities. And we implemented that, and yeah, it works. So there are two kind of representations of the short authentication string, one for 16-bit and one for 20 bits. That's shown here, and yeah, not many tries are needed to crack this, obviously. This has been fixed in Linphone. Okay, so next attack. So if you do this Diffie-Hellman key exchange with ZRTP, and you press the confirm button that your short authentication string is the right one, ZRTP stores this inside a cache. So the next time you do a call to the same person, you no longer need to compare short authentication strings because you did it in the first call. This is stored inside the cache. And next time they just use what is inside the cache, do a key derivation on it. So it's like similar to like self-healing properties. Okay, so there is a special scenario here, what is also written in the RFC. I just read it out. If either party discovers a cache mismatch, the user agent who makes this discovery must treat this as a possible security event and must alert their own user that there is a heightened risk of a man-in-the-middle attack. So this means if Alice does a call to Bob, the secret is saved. Second call to Bob, and Alice looks into the cache, and there is a cache mismatch. So this doesn't fit to the one that is used by Bob. Then there is maybe a security incident here, and there is security warning in Jitsi. This is displayed here. An expected retained shared secret is missing. I don't think anybody end user would understand what it's saying here, but they implemented it. At least it's a must in the RFC. So I think it's a questionable requirement because end users maybe just dismiss it. CSIP Simple and Linphone do not implement this. And while checking this out, we found a bug in Jitsi. So actually, they not just show this on a cache mismatch. They also show this if there is just one entry inside the cache and they're creating a second entry. They also show this flag because there was one missing initiation of an object here. So we fixed that. So the security warning was raised for other participants, new clients of Bob. So, and nobody complained. So, okay, let's just. So, last attack I want to present in the presentation. That's what we call the shared man-in-the-middle attack. So, let's consider the following. Like, Alice, Bob, and Eve are friends. They know each other. They talk a lot on phone. So when Alice and Eve do a normal phone call, they both confirm the short authentication string. The shared secret is stored inside the cache on both sides. So pretty nice. Second time, they don't need to confirm the short authentication string. Then there is a call between Eve and Bob. Same thing happens. They both confirm the SAS. Everything is correct, nice. Second call, no need to check SAS. And the third step, Eve is now evil. Eve is conducting a man-in-the-middle attack, like we showed in the beginning, like an evil operator. And it's just placing herself in the middle between Alice and Bob. And yeah, actually it works because there are shared secrets between Alice and Eve and with Eve and Bob. So no SAS confirmation required. Everything works. And also the zip addresses shown on Alice's phone shows Bob at example.com and on Bob's shown Alice. So what is missing here? I mean, it's a pretty obvious attack. Why does this work? So in ZRTP, there is no binding of the identities used in ZRTP to the outer protocol. So they explicitly designed ZRTP to work independently of the session protocol. So the cache lookup just uses the ZRTP ID, which is just a random ID. It's not the zip address. So yeah, this works. So in Signal, there is no cache. You cannot confirm it, so it's secure. Acrobat Softphone, they actually implement the RFC compliant protection. Again, the RFC knows about this somehow. And you can actually enter a string for the participants. And that is stored besides the ZRTP ID inside the cache. And if you do a second call, this is like the zip address, it's Alice. And this is the ZRTP ID. So there's a mismatch here. But I mean, the user needs to see this, right? It's even, I mean, I don't think I say if you would do a usability study, I'm not sure people will even get why they need to enter a name here. So, and the other implementations are insecure. There's no way to see which ZRTP ID is used. Okay, I have some time left, right? Oh, that's good. So I will do a short quiz. Okay, security indicators. That's also a nice topic. We just looked briefly at security indicators and the applications. We did no user study, but just we will do now a short user study with you. Okay, so what is end-to-end secure, left or right? Who's for left? Who's for right? Okay, maybe for left first. Left, hands up for left. Okay, right. Okay, yeah. Okay, this was easy. This is end-to-end secure. It's a green lock icon, right? This is an open lock, but it's red. So okay, that is easy. This is Jitsi, by the way. Okay, this is more difficult. Okay, which one is end-to-end secure? Who is for left?
24 seconds.
Who's for right? Okay, yeah, you can see there is a cross inside the lock, right, on the top. So this is insecure. This is, I mean, even there is a green icon, but that doesn't have to do anything with security. So just the lock. I mean, it's a closed lock with a cross. I don't know. Okay, last one. What is secure? What is insecure? Who's for left? Who's for right? Okay. What about this? Yes. We were also quite confused and we couldn't really reproduce this. But we asked the support about this, and actually this says that. Now it comes the following. So we have that ZRTP for the voice communication, and for the video it's clear. It's not encrypted. But there is no voice, there is no like long click or information what is for what, and yeah, it's really confusing. Okay, so that's it. Come to my conclusion. Current status, LIN phone has been fixed. The bug in Jitsi we fixed directly upstream. That's what was really pretty easy. Signal longer uses ZRTP. This is an independent decision of Moxie, it has not been influenced by our research. It's been done in parallel. Yeah, and for the future, most apps fall back to insecure mode if the ZRTP fails, and if you think about the security indicators, I don't think you will notice. Shared man in the middle tag needs to be discussed, and yeah, that's it. Thanks.